on the market, price and quantities are determined simultaneously. In the model we have estimated with OLS, it is as if we are saying, first we have the price, and then the price causes the quantity. It's not actually, we're not actually capturing the way the market for gasoline works. And this simple example says if we have a supply equation like this, from the supply equation you simply derive an expression from the price, and you go computing the covariance between the price and the error term of my demand equation model. You find after some computation, you can replicate this computation by hand. But at the end of the day, you realize that we have a non-zero number. Okay, this correlation is different from zero. So the implication is that the estimated beta 2 parameter, which is the elasticity of demand to the price, is not consistent. So recall that the number we had in the graph here, in the estimated model was, so my point is that I am questioning the validity of this elasticity, minus 0.22, even if the model looks wonderful, but it looks wonderful under the assumption that, say, prices causes quantity. But in a market, we know that price causes quantity, but quantity causes prices, because the two price and quantities are determined simultaneously. Okay, guys? So understand what is my issue, my concern? So starting from today, in our last classes, we are going to discuss this problem, this kind of problems, which involves, so we are stopping thinking about causality running from the right-hand side of the equation to the left, which is what implicity holds when you push the button OLS, and we start thinking in a more general way. We start thinking about causality, relationship between the variables. Okay? So what I do now is moving to the slides again, and let's now you can understand very well what I mean. Okay? So our topic is endogeneity issues. So what do we mean by that? We start from our linear regression model. Can I stand up? I don't know if probably they don't see me. If I stand up, probably you don't see me. But maybe we change the camera. No, you didn't see it like this. At the center, of course. They should see me this way. Yes. So, is it okay, Tom, if you see me this way, or you prefer the other way?
No problem for me.
Thank you. Okay. Anyway, if you don't follow me, let me know. But anyway, so this is the model. It is our linear regression model, and I'm using the index, and we know that the crucial condition when we push the button OLS. And in this model, we estimate typically the beta, the slope parameters beta and sigma square epsilon, because I have in mind the classic linear regression model. And even if I realize that I have some heteroscedasticity, but I cannot model heteroscedasticity, even if I realize that I have some correlation, but I cannot model a correlation, provided I know there is absence of correlation between the regressor and the error term, we estimate the model by OLS. Okay? And we know that for the OLS to be unbiased in small and large sample and consistent in large sample, we know that the correlation between the regressors and the error term must be equal to 0. And now we know that this very well, okay? So, when we run OLS, we have in mind a setup where causality runs from the regressors to the dependent variable, and of course the link between the two is given by the beta coefficient. But we are now understanding that this is not always the case. With the example with our demand model for gasoline consumption, if we think that the price, of course, I could be an expert of energy market who say, no, guys, energy market work like this. For some reason, you first have the price and then quantities are determined. Could be, I don't know actually if it work like this, but my intuition as an economist suggests that price and quantities are determined simultaneously in the market. Unless you have a very specific model that says otherwise, okay? So, the causal interpretation, say, regressors cause yt is valid, say, is valid, I mean, when we can claim that the expected value of the error term conditioning the regressor is equal to 0. And we know that by the law of iterate expectation, if this is true, then also the unconditional expectation, of course, will be equal to 0. Indeed, if you come back on our very first slides, you will find, again, this concept, okay? This was our starting point. Come back on the first set of slides, if you don't believe me. And under this condition, we have that we can interpret, say, the regression model as a model for the conditional expectation, okay? And this model implies that in order to predict y, if I have to make a prediction on the quantity, the demand, the quantity of gasoline, I only have to know the price and the income. That is the implicit interpretation. And if we have a situation where, on the other hand, if we find that the expected value of the error term conditioning on the regressor is different from 0, in a sense, what is the interpretation of this expression? The interpretation is that there is some kind of link between the error, I mean, the regressors affect the error term. The regressor says something not only on y, but also on the error term. So the price of gasoline not only determines the quantity of gasoline, but also say the demand shock. That is the point. So if we have a situation like this, where this conditional expectation is different from 0, we understand that my forecast, my prediction of y given the x's will be no longer equal to this term here, but plus, I have to take into account this element, which is different from 0. So it means that the knowledge of the regressors is not sufficient alone to predict y. The point is that I need to model both prices and quantities and prices in order to make prediction on the quantities. I cannot assume that I can predict the quantity just focusing on the demand equation. I also need to know something about the supply equation. That is the message. And so what is the problem that we have with the OLS? Why the OLS estimator does not work in that case? I want to come back on this issue, which is very, very important. So we have been working on the fact that we can factorize. We can write the beta estimator, the OLS estimator, like the true value, plus something. We have done quite a lot of work on that. Come back on the recording of the classes, okay? I'm not joking, I'm serious. And, of course, we can express this quantity here like using notation based on the index, like with this summation here. which is the one I'm touching with my hands here, okay? And the other term here can be expressed like this. Of course, since there is -1 here, 1 over n, and you can kill 1 over n and 1 over n. But why is it useful having 1 over n here? Because what is the argument behind the consistency of the OLS estimator? The point is that if we send n to infinity, we have a large sample. The point is that under regularity condition, this sample, this kind of sample mean, should converge. It's a convergence in probability, which means the probability that this sum becomes closer and closer to the population counterpart. So I'm simply replacing the sum, the average, with expected value. Okay? So if n goes to infinity, I know that this term converges to expected value of regressor prime, which is, this is kind of second order moments of the regressor. It's not something strange. It looks something mysterious and strange, but it is not. If you are in your regression, if you have just one regressor in your model, this simply would be the expected value of the square of the regressor. So it's kind of variance of the regressor. So it's not complicated. But the very important element is the second one. If the second one, again, converges in probability to what? To the expected value. So I replace the average with expectation. And now you understand that if this expected value here is equal to 0, when n goes to infinity, when n gets larger, you have that the beta or less estimator is equal to the true value plus something which goes to 0. But on the other hand, if we know that this object here is different from 0, so we have correlation between some of the regressors and the other term, we are in trouble because regardless of the length of the sample, even if we send n to infinity, we have that, say, beta or less estimator will be true value plus something which does not disappear. It will remain there. We have a bias. Also asymptotically, also when n goes to infinity. And so the estimated elasticity of demand of the gasoline with respect to price will be a number, a meaningless number. So the point is the minus 0.21 we have estimated in our beautiful model by OLS could not reflect the actual elasticity. Could be lower. So if we, for instance, if we want to impose some, for instance, if we, the example could be stupid. If we want to use the estimated model to put on some policy, we could do a mistake because minus 0.21 might not be the actual elasticity of the demand of gasoline with respect to price in the US. Now, as a general rule, we call the regressors that are not uncorrelated with the error term and that make the OLS estimator not consistent are called endogenous regressors. So now, coming back to our example, I had the suspect that the price of gasoline in the equation we have estimated, the price of gasoline could be an endogenous regressor. It could be correlated with the error term, which in our model could be interpreted as a demand shock. So the price could be correlated with the demand shock, which makes sense if prices and quantities are determined simultaneously on the market. Okay? Let me consider another example. Our starting example was based on time series. Now let me come back on, let me go to a cross-section example. And we also know very well this example. It is, you remember the model, we estimated a model of 20 Italian regions. So n small, n equal to 20. And this model we regress, say, per capita consumption in region I over a constant and over disposable income of region I plus error term, okay? But now, and we did OLS, we estimated B1 and B2 by OLS. What could be the suspect here? I could say, well, but at the end of the day, what is disposable income? Disposable income of one people is that, say, I get my, imagine that it is equal to labor income, say, of what I do with my labor income. I will consume part of it and I will save part of it. So, in a sense, disposable income also depends on consumption. Yes, depends on consumption plus saving. This is an identity in economics. It's simply a very simple identity. But there is a second equation. That is the information we have. And in this case, so let me check whether, if it is the case, if actually the model is like this, okay, then let me compute whether, say, this regressor is correlated or uncorrelated with the error term. So I go computing the expected value between disposable income and the error term. So I replace disposable income with this expression here. So I have this, okay? And then I go on with the linearity of the expected value. So I have to compute the expected value of per capita consumption times the error plus saving times the error. Now, just to simplify our computation, let's assume that we know from our theoretical model, we know that there is no correlation between, say, saving and we assume that saving is completely exogenous, given. So we can put this element here to 0. Okay? So given this simplified, it's simply a simplification. It's not more. Then the correlation between regressor and the error term will be equal, will collapse to only to this number here. And now what I do? What should I do to compute this number? I replace CI with the model. CI is given by this expression here. So I replace it here, okay? I go on with computations, and I understand that the expected value of beta 1 times epsilon 1 is equal to 0. I get this expression. Okay, so I have beta 2 expected value of disposable income times the error, and then I have, say, the expected value of error squared. Okay, and so I can bring this guy on the left-hand side. Okay, I get this expression, and at the end of the day, I realize that the correlation between the regressor, disposable income, and the error term under the assumption we have. I mean, if disposable income is given by the sum of consumption plus saving, and assuming that saving is uncorrelated with the error term, we get this number, okay? Which suggests that also in this case, disposable income could be an endogenous regressor. In the sense, what is the issue? The issue is that, yes, it's right that income determines our consumption. This is what this model says that income determines consumption, but the second equation, the second edge say that consumption in turn is part of the income. So, in a sense, the first equation does not explain only consumption, but only income. And that is the circularity, causality issue that we have in this kind of models. And we know that in these cases, we have an endogenous regressor, and the OLS estimator will be. So if I run OLS, if I estimate the beta 2 coefficient by OLS, I know that the beta 2 output will be true value plus a bias, of course, which will never be, even if I have 20 billion regions rather than 20, the bias will not disappear, will be there. So even with infinite information, we get a wrong estimate, a wrong number, which is the Worst, having, say, an estimator which is not consistent is the worst case for an econometrician. So the minimum requirement for an estimator to be good is a consistency. So what to do? So next week we are going to discuss we try to address the following question: what we have to do in these cases, and let's discuss in words for the moment what we have to do. And I want also to give you the intuition, sticking to the example of the 20 Italian regions. I want to give you the intuition on how we can address the issue. Then we stop, we take a break, and then we make the survey. You have to make the survey, okay? And then we go home. It's Friday, okay? You got to have your beer, and, okay? Your deserved beer.
Beers.
Sorry?
Beers.
Beers, yeah. You're definitely right. I still cannot come with you with the beers, not yet. I still need to recover. So what is the natural solution? The solution we have in mind when we have endogenous regressor is to find a way to remove the correlation between the endogenous regressors. The endogenous regressor might be one, but we could have more than one, okay? We have to remove this correlation and the disturbance there. Once we do that, we can come back to LS. But we have to manipulate a little bit the model. Let me give you the intuition, okay? One possible solution to the problem. Imagine that we know that the regional per capita disposable income is correlated with the previous year per capita disposable income. That is, imagine that disposable income in region I is alpha times disposable income in region I, but in the previous year, okay? Plus an error term. So this element, this V I'm touching with my hand, is kind of, say, is an error term, okay? So imagine that I know that disposable income can be in 95, for instance. Our data set, we have a cross-section of consumption and income dated in 95, okay? And then we'll see, we come back on the data. Imagine that disposable income in 5 in region I, region Abruzzo, is related to disposable income of 94 plus an error term, which can be quite reasonable, okay? Now, we understand that if this is the model, if this model is true, we can understand that, so in this model, we can, first of all, let's think about this equation. This equation, we can't rule out causality running from disposable income of 94, causality in this model runs from the past to the present. I mean, disposable income in 94 affects disposable income in 95, but the other way is not true, you understand? So, in this model, the advantage is that causality runs just one way. Do you agree on that, guys? It is impossible that income of 95 causes income in 94. Okay? So the point is, if this is true, we can say that disposable income in 94, so with -1 here, causes disposable income in 95, but the reverse is not true, okay? When causality runs just one way, we call the variable predetermined, okay? Now, what we do now? What I can do, I can estimate the alpha parameter of this model by OLS. We don't have any endogenous regressor issue here. So OLS, in this case, will be a good estimator of alpha. And the alpha, please recall that alpha captures the link between say, the endogenous regressor and the predetermined regressor, okay? So what I can do, I can estimate this model, this auxiliary model by OLS. I get alpha at by OLS, and then I could say, well, now if once I estimate the model by OLS, I get the fitted and get the residual. We know this, right? What is the fitted? The fitted will be the estimated alpha times the income in 94 of the region, and the residual will be the difference between, say, the true income and the income predicted by my model, okay? And one thing we have to keep in mind is that by construction, because OLS, the fitted and the residual are uncorrelated by construction. They are orthogonal. The OLS method is such that basically the fitted and the residual are uncorrelated. Okay? It's just a computational issue. Okay, so coming back, what I said, I want to summarize what I said, what we did. I said, okay, I have an auxiliary model, so I have some more information. And the auxiliary model says that disposable income in 95 might depend on disposable income in 94, plus an error term. I know that this model, alpha, can be safely estimated by OLS, because causality just runs from the past to the present. So if I can do that, I estimate this model by OLS, and I get fitted and residual. And please notice that the fitted is a function of the predetermined variable. Now, what I do, my objective was estimating beta 2. Recall that I wanted this. So what I do, I come back to my equation, and now I add and I subtract the follow quantity on the right-hand side. What do I add and what do I subtract? I add beta 2 times fitted, no longer disposable income, but the fitted from the previous equation, minus beta 2 fitted from the previous equation, plus error term. You see, I'm not changing the model. This is just a reparameterization. I'm writing the model in a different way. But I'm not changing the model because I have added and subtracted the same object on the right-hand side. Okay? Algebra allows me to do that. Then I rewrite the model like this. I say, okay, I write my new regressor now is no longer disposable income, but disposable income fitted from the previous model. And then I have the error term. And then I rearrange the model like this. I have beta 2 times this difference here. You should agree with me. It is the residual of the previous regression. And notice that we know by construction that this fitted and this residual are uncorrelated by construction. And my last point is this new residual fitted is uncorrelated with the error term epsilon I. Why? Because it depends on the past. It depends on past income. I know that past income cannot be caused by current consumption. I can't capture I took into account the causality link. So what I've done, I rewrite this model. Simply, I rearrange this equation like this. I call UI this term here. It's my new error, okay, error term. But what is the advantage now? That I know that in this model, this regressor and the novel error term are uncorrelated by construction. So, what I do now, I can re-estimate this model. I can now estimate beta 2 by OLS. But my novel regressor will be no longer disposable income, but the fitted from the previous model. So we are applying, if you think about it, we are applying OLS twice. First, in the auxiliary model, from where we get the fitted, and then in the second transformer model. And we have done this job in order to eliminate the correlation between. So this regressor is no longer YD, it's YD fitted. A YD fitted is no longer, a bioconstruction is no longer correlated with the error term. So we can run OLS to estimate beta 2. And since we, don't worry because next Monday I will start from this, but since we are applying OLS twice, the estimator we are building is called in two-step or two-stage least square. The acronym is 2SLS, and Gretel calls this estimator of TSLS. Okay, sorry, but it would be two-square least square. Yes, two-stage least square. Okay, so we are applying OLS twice. Why twice? We applied OLS to this auxiliary model, where we estimated alpha consistently because we know that this regressor is uncorrelated with the error term by construction. And then we come back to the original model, we manipulated it, and we know that in this manipulated model, there is no longer correlation between this regressor and the error term. And so we can run OLS in a second step. So let's keep this in mind. Next Monday I will start again from, I will start exactly from this example. Then we're moving to, I've not forgotten our gas oil consumption model. I want to come back on that. We check whether, say, we can, you understand that, let me just, before I stop, let me say, give you one intuitive way about thinking whether we are doing well or not. So imagine that I come back to my original model, this one, and I estimate this one, the model was this, example. Okay, imagine that I come back to my original model, and as we have done, as we did, I estimate beta 2 by OLS, okay? And I get some number. I do my transformation, so I do OLS now in this manipulated model, okay? And apply OLS in this second model. And if I realize that the beta 2 estimated with OLS and with the two-stage least square, if the values of beta 2 are very different, what is the message? And what is the message if the values are very close to each other on the other hand? What is the way we can interpret the outcome?
Can you repeat it?
Yeah, my point is that imagine that I estimate beta 2. Oh, let me go on the data so you. Now I open a new, this Italian region 95. I sent you the data set this morning, okay? As a magic, you have, say, if you can find that we have consumption 95, cross-section 20, per capita consumption in the 20 Italian regions, and I have, say, income 95 of the 20 Italian regions. And the model we estimated by OLS was something like, we estimated consumption in 95 as a function of constant and income in 95. If you remember, we checked that we don't need robust standard errors because we tested the stochasticity, blah, blah, blah. So the estimated beta 2 coefficient in this model is 0.55, okay? Now, I do what I said in theory on the slide, I do on Gretel, but don't worry to understand because we'll come back on that. So I will get a novel estimate of beta 2 with a different method, and to get that estimate, I do the following job. I show you. Oh, sorry, I have to increase the font. Tools, preferences, font scale 20. Okay, So the model estimated by OLS is this: consumption 95, constant income 95. Okay, I click OK, and this is the estimated model. Blah blah blah. We can check that all coefficient looks significant. Please recall that in this case we are dealing with a small sample, so we need the small sample theory for testing hypothesis, that we need normality, blah, 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 okay? Now, I have the suspect that, say, income might be an endogenous regressor for the reason that we said. And if I look at the data, for instance, I realize that income in 95 and income in 94 in the previous year among the 20 Italian region, if I compute a correlation, I find that they are very, very strongly correlated, okay? So, I'll do the following. I move to a new estimator, two-stage least square, but don't worry, we'll come back Monday on the theory, so you will fully understand what I'm doing, okay? And what I have to do, the dependent variable is consumption 95, those are the regressors. Look, I have a new box here, instruments. That's why the estimator we get is called instrumental variable estimator. And what I do, I want to instrument income in 95 with income 94, which is highly correlated. We have seen the two variables are highly correlated. But the advantage of this variable is that income 94 cannot be an endogenous regressor in the model for consumption in 95 for the causality issue we have been discussing. So now click OK, and we skip all, for the moment, say the test, the part of the output. I want to focus your attention, to pose your attention on the estimated coefficient obtained this way, which is 0.55. With OLS, we got 0.55. With the instrumental variable, we get with two-stage least square. Instrumental variable, two-stage least square will be the same thing, but we have still 6 hours to work on this topic, so don't worry. So my intuition is, well, 0.55 with instrumental variable, 0.55 with OLS, so it seems that things do not change in an important way. Look at the constant, 1.20, 1.21. So what could I conclude?
The fitted estimator is good. It's close to...
Yeah, but my point is we learn to look at the following test called Hausmann test. Look at it. Null hypothesis. OLS estimates are consistent. And now, regardless of how it works, we know that when we know the null, three ingredients: null hypothesis, test statistic, which is chi-square 1 distributed under the null, 0.84, and p-value 0.35. Do we reject or we accept the null? That the OLS estimator are consistent in this case. We accept, of course, but I could see that already. Look at come back, 0.55 OLS estimator, 0.55 IV estimator, and it does not change very much moving from one estimator to the other. So the message seems to be, you don't need to use an estimator different from OLS in this particular case, in this example.
I have a question.
Yeah.
In this, can we say that income is not endogenously affecting the model?
It seems that, we don't need to make an adjustment to, the message from this estimation is exactly as you said. Yeah. But let me now move very quickly, very fast to I'll do the same exercise on the gas oil consumption model. Of course, we'll come back on that, but I want to give you the intuition, okay? So I come back to the previous model. I open again gas oil consumption, okay? And let me increase the font. Tools, preferences, font scale, 20. Please don't just follow me what I do, okay? Not important. We are coming back on this issue. Now, what I do, the model we estimated by OLS was apparently a wonderful one. I had the growth rate of gasoline consumption, the dependent. I had the growth rate of income. I had the growth rate of price of gasoline consumption. This was my OLS estimate, okay? Now, my concern is that this regressor could be an endogenous regressor because quantity and prices are determined simultaneously. So for the reason we've been discussing, I have a problem with this coefficient. Now, what I do, I also apply the two-stage least square estimator in this case. I will select some instrument that we'll discuss next week, so don't worry. But I do an instrumental variable, two-stage least square, so my model is different gasoline consumption. You can see up to this point is exactly the OLS model. Okay. Now I have to select some instruments. Instrument will be variables which are uncorrelated with the error term of the model, but are correlated with the regressors. Okay. This will be the trick the device we are going to think about. So what I do now, say, okay, constant. We don't need it, just the constant. I don't have endogenous regressor issue for total expenditure because total expenditure is very large, includes very many objects, and the consumption of gasoline just a very small part of it. So I don't expect causality running in both ways. I expect causality running for total expenditure to gasoline consumption, but not the other way. Okay, so I'm quite safe that I can replace. I will use the variable itself as an instrument for total expenditure. Now I need some variables which are related, which are uncorrelated with the error term from a theoretical point of view, and are correlated with this regressor. I do the following exercise. I put in the data set, I have the growth rate of the price of non-durable consumption, a very general item, non-durables. You know, consumption, you have durable goods and non-durable ones, okay? I put this one as an instrument, a variable which is related to the price of gasoline, and then I also want to put the price of gasoline, but I will date it at t-1, otherwise I am in trouble. So I use lag. I said in the instrument set, I want to instrument the price of gasoline with the price of gasoline in the previous quarter. Okay? I click OK, and look, I have say 3 regressors, and I have say 4 instruments. I click OK, and then I'll stop the promise. And what I observed that in this estimate now, the sign of the coefficient is still in line with the theory, but I have a drop in the elasticity of gasoline consumption. It is significant. You can see the T ratio, but they have a drop from minus 0.21 to minus 0.17, and we learn to look at this Hausmann test. So in this case, even if we don't know very well the Hausmann test, but just simply looking at the output, we know that in this case, we reject the null hypothesis that the OLS estimator is consistent in this setup. But what was the intuition? I wanted the intuition. The intuition is that I see that minus 0.17, so it's almost 18, but is quite different from minus 0.21. And the larger the difference, you will find that the test we have here will be rejecting consistent, which means making your adjustment, making your two-stage least square make a difference in the estimate of the coefficient. If it does not, of course, you don't need to change your estimate. Okay, let's stop for the moment here, but our next classes will be on, say, refining this concept, giving a more formalized theory about instrumental variable, but now you have the intuition. You get the intuition, but we'll discuss that seriously. Now, I ask you this favor. Before stopping, let's do the questionnaire, the survey, okay? So let me take, so I ask you to stay here, and also students at home, please. We are finished quite early today, but in return we have to do this, okay? We are asked to do this. Opinione, student. So I have to open a package. Okay. So guys, please stay here. I have to ask you to stay here because it is important. What is going on in my mobile telephone? Is it the Wi-Fi working? Let's see. Okay, I will use the data. Okay. Okay. Now using the data, it works. I hope so. We can stop recording for the moment. Okay, it's done. But do you also have problems with the net, with the internet? I have problems with my mobile and both the. Adesso ci riesco a capire. Please stay connected, please. Non so cazzo sta capire cosa succede. Can you wait a couple of minutes? I go back to recover perché non ricordo come fare. Okay, we do that Monday, next Monday, because I don't know how to solve it. We can go on.